Good job. There you are. We were about to start without you. Okay, well, good afternoon, everyone. I'm glad you are all here. Can you set that on the desk outside? Thank you. Okay. I've had some strawberry fancy shake thing spill on the carpet before, so I'm very wary of any and all non-water drinks, okay? So, anyways, we've got fun stuff today. We are going outside. Yes. What? You don't like outside? Okay, well, not yet, not yet. Yes, you can take the drink with you when we do that. We're not there yet. We gotta get ready. What we're going to do is, our mission is to measure the height of the flagpole. Okay? So, we're gonna send Leo up to the top. No, we're not doing that. We're going to use geometry to make it way easier, okay? You don't want to try climbing that thing. It's terrible, okay? So, those of you at home watching the video, unfortunately you are not here. You don't get to experience this with us, but you can still do this yourself. The full instructions are there on Google Classroom. I've got a link to how you can build the little device that is this guy right here. Right? This is called a clinometer. It measures incline, so inclinometer, right? And you can make this yourself at home, just with paper, straw, tape, string. And I used binder clips here. You can washer or some kind of weight just to make it, dangle properly. And that's all we're going to need. This plus measuring tape. And we can measure the height of anything, a building, flagpole, tree in your backyard, right? Without actually having to reach the top of it. Right? Here's how we're going to do that. I have a diagram prepared for us here. All right? The easiest thing we can measure, I think you will all agree, would be this, right? Your horizontal distance from the flagpole. That's easy to do, yes? All right, take a minute. We can do that part. Simple enough. But what's not as easy is measuring the actual height of the pole, because you got to somehow get to the top. You got to hold one end of the tape measure up there. Okay? Or you could also measure, right, from you to the top of the flagpole. Right? We've got that diagonal of a triangle in there. Theoretically, you could measure that. That's not that easy to do directly either. We want the easiest possible. But notice, what have I drawn in here? If I connect you to the top of the flagpole, I create what shape now? A triangle. So at the very least, we could, right, let me draw this one in up here. The flagpole is perpendicular to the ground. So if we draw a line here that's parallel to the ground, just straight from you, you could find, let's call this piece Y, and you are however tall. Okay, well, not everybody is 6 feet, right? But you could at least see this, right? If we could somehow measure from you to the top of the flagpole, we could add that to your height and get the total height of the flagpole, yes? You guys see that part? That's the last step. Okay, I'm working a little bit backwards here. I want you to realize that's the last step. We can measure from you to the top of the flagpole, and then add your height. We'll have the total height from the ground. How do we get this if the only thing we know is the horizontal distance? It's a trick question. It's impossible. If that's the only thing you know, you can't do it. But if we had one other piece of information, we had this angle here. I'll call it alpha. Then we could find that height. Okay? And there's actually several ways to do this. The more general solution would be to use trigonometric ratios, and we could solve that for any angle that we want. We don't have the trigonometric ratios yet. We haven't learned that bit. Okay? We're not going to get to them this year. We'll save those for next year. Right? They're very handy. But what we do have, something we have studied in this class, is the special triangles, right? We've got Pythagorean theorem. If we had the two lengths, if we had the hypotenuse somehow, if we had these two lengths, we could find that one, right? Pythagorean theorem, could get the third side. The special right triangles let us take one length and one angle and solve for everything else. That's what we're going to take advantage of. So we are purposely going to set that angle to be one of our special triangles. And there's two different versions. Either alpha is 45 degrees, gives us our 45, 45, 90 right triangle. Let me make it a little bit bigger. Okay. Right, we have that one. Or we could do 60 degrees and have a 30, 60, 90 triangle. With me so far? Right? We could make one of these special right triangles, and then we could figure out what the other one is. One of these is easier than the other. Neither of them is too bad, but the 45 is going to be simpler. Because if this is a right angle, and this angle is 45 degrees, what is the measure of that angle? (45 degrees). That's why we call it the 45, 45, 90. 45 appears twice. It's symmetric, right? In fact, this is not just any right triangle, it is the isosceles right triangle. You guys remember what isosceles means? Two equal sides, thank you. We took so long to figure that out in fourth period, thank you. Two equal sides. If this side is, say, 10 feet long, what does that mean about the other sides? Which one? Not the hypotenuse, this one. Because look at 10 feet is across from 45, right? So the other one needs to be across from 45. So this guy is also 10 feet. All right, just for completeness sake, we will note that this side would be 10 times the square root of 2 feet. Would be the hypotenuse length, but we don't need that. We're trying to find the height of the flagpole. Couldn't this be the height of our flagpole? And wouldn't this be the distance we're standing from it? They're exactly the same, right? So if we can manage to set our angle to 45 degrees, our height measurement is the same as our horizontal measurement. No computation required. Just copy one over. You do have to add your height, right? Because we're measuring from you up. That's it. Simple, right? Yes, agree? Any questions on how we would do that? So the only thing that remains is how do we set the angle to be 45 degrees? I'll get to that. Now I want to take a look at the alternative. What if you can't manage a 45-degree angle? What if you don't have the space to stand a distance away equal to the thing's height? Right? If you're limited, if you're cramped, right? You've got a very small backyard but a very tall tree. I'm like, I can't get that far enough away to make a 45-degree angle. Maybe you could manage a 60-degree angle. Okay? Maybe you could stand here. Okay? This is our 90. This would be 60. This guy ends up being the 30-degree angle. And so if this is 10 feet, do you guys know what the height would be? What's the relationship between the legs in a 30, 60, 90 triangle? The This is why we added it to our notes, so we can look this up and check, right? The shortest possible side is always across from the 30-degree angle. That's what we have here. So it's going to be more than 10. And the longest side is the hypotenuse, right? Across from the 90. That guy's going to be double 10. 10 times 2, or in this case, 20 feet. So this has to be somewhere in between. We need to multiply 10 by something that's more than 1 but less than 2. Anyone remember what that number is? What's that? No? It was one of those weird looking things. It was that irrational number. Square root of 3. Okay? So if this is the situation you find yourself in, I can't get a 45. I have to use the 30, 60, 90 right triangle. Then you have to take your horizontal distance and multiply it by square root of 3 to get your vertical. And that's your measurement. You then add on your own height, and now you have the total height of the building or the tree or the other flagpole, right? Not too bad. It's one extra step. That's it. It's not even that bad. Any questions on how to do that? Right. Our plan today, I'm going to send you outside to take the measurements, and then we'll come back in. You have to do this calculation. Okay? Given the choice, we're going to pick the easiest route, right? We are lazy mathematicians. Okay? We're going to pick 45. It's also the easiest one to set, because I can make a simple clinometer at home just from a sheet of paper. Okay? And that's what I did. I took a piece of, well, this is actually one of those like divider tab things to go in your binder, because it's a little bit thicker paper. Okay? I folded a diagonal to make a square, and now this is a 45, 45, 90 triangle. I decided it was a little too big, so then I cut it in half and made a smaller 45, 45, 90 triangle. Tape a straw to it, dangle a string from one corner, and so long as that string is perfectly parallel to that side, I've made a little mark down here to know it's definitely there, then I know this is sitting flat with the horizon, and looking through this straw, it points perfectly at a 45-degree angle. So all I need to do is take my clinometer and look through the straw at what I'm looking for. Be like, I want to find the height of that thing over there. Okay, look through the straw at that thing. How is my string doing? Well, it's too far. I need to tilt up, so I got to get closer, right? And as I move closer, staring at the object, right, I tilt further and further back, right? By the time I'm standing at the point where this string dangles right in front of that black mark, I know I'm looking up at a 45-degree angle. That's how our simple clinometer works. It has one angle set. You could make a more complex clinometer here. If you used a whole protractor instead of just a piece of paper, then you could measure up to any angle you wanted, right? In fact, you could stand anywhere and measure what the angle is and use, again, more advanced trig to figure out the rest. We're going simple version today. Okay. Any questions then on how to use this? So the string tells you what the angle is, right? There is always an angle between the straw and the string. Okay? That angle is 45 degrees when the string hangs at the black mark that I've made on the paper. Okay? Which I only added the black mark just to make it clear and easily visible. But the idea is that the string is now vertical, which you can see on the vertical side of the paper. So when it's in line with that, it will be at the black mark on the bottom, right? And thus making a 45-degree angle here, which means it's a 45-degree angle here that tells you, yes, this is parallel to the ground, and looking through the straw is at a 45. So you're going to go out there and you're going to pick somewhere to stand. Okay, there's the top of the flagpole. Hold it up to your eye. Try not to poke yourself in the eye. Okay, I did nip the tip off of this so it's not quite as pointy. Okay, hold that up there, look through, and oh, that's not out of 45 yet. Okay, take a couple steps closer. Is that out of 45? Right? And you're going to maneuver around until you get this to dangle right there. Okay? It'll be a little tricky. It's a bit windy out, so it might blow around a bit. Okay, so try to block the wind, try to control it, try to get the best measurement you can. And then from your position, where you're standing, we'll measure from you to the flagpole. That's the measurement you need. All right? Good there? Excellent. Okay, so that will do it for video there. It's time for us to go out and take measurements. You will need a clinometer. There should be enough for one for everybody. You will need some way to record your measurement. Right? So whether that is paper and pencil, or if you can take notes on your phone, you can just type in to your note app on your phone, I am 23 feet and 7 inches away. Right? Save that number somehow. So then when you come back into the room, you can computation. And then when we're back here, if anybody needs to measure their height because they don't remember how tall they are, we can do that too. Okay? You run your measurement, and then the only thing to do is to put your final answer to the post on Google Classroom.